which is the Schwarzschild solution. And the basic philosophy here is that we know Einstein equations now, and we know that the equations tell us r mu nu minus a half g mu nu r is equal to 8 pi g t mu nu. But we don't know if this equation has any exact solutions. It could be that it has only approximate solutions, and Einstein in fact thought that would be the case. Of course, finding approximate solutions is not going to be difficult, because we know that in a situation where Newtonian physics is right, there's an approximate solution. We've seen this very early in this course. Take the metric ds squared equals minus, I think 1 plus 2 phi dt squared plus 1 minus 2 phi dx squared plus dy squared plus dz squared, where phi is any valid Newtonian potential that solves the Newtonian equations del squared phi equals rho, for pi rho or whatever it is. Okay, once we know that, then we know that this is going to be an approximate solution of these equations for the corresponding energy momentum tensor whose 0, 0 component is that density rho. If you remember, that's the whole way that we constructed Einstein's equations, starting with Newtonian equations and asking what's the minimal generalization which preserves the Newtonian results. Okay, we don't look for new theories which contradict old theories which are already tested. This theory doesn't contradict that Newtonian gravity, it extends it in a certain way. In some areas it contradicts it, but for weak fields at large distances away from gravitating bodies, Newtonian gravity is still correct. Okay, so this is an approximate solution. Question is, so one assumes that Einstein knew this fact, and without any more work we can also take a particularly simple example. The simple example in Newtonian physics would be to just take rho equals 0. So the density, which is the source of the Newton equations, is taken to 0, 0. So therefore the Newton equation reduces to del squared phi equals 0. Okay, that's an equation. And of course it has the obvious solution that phi is equal to 0. But it has lots more solutions, and in general the solutions are phi is equal to, up to some proportionality constant, in fact no proportionality constant, is equal to minus gm upon r. Okay. Now here's an interesting physical fact which we should give a little thought to. We all know it, but it's still worth giving a thought. How on earth can I take an equation which just says that divergence of phi is 0 in some region of space which has no energy at all, there is no source, and come up with a solution like this? It seems very counterintuitive. Okay. At the same time, it's also true, because if we did have a body which had an energy density, a mass, and we went far away or just outside the body, we would be in empty space, but we would see such a gravitational potential. Okay. So even in empty space there can be a gravitational potential, and in fact the most general thing that you expect if the object itself is spherically symmetric is that outside it you get this kind of gravitational potential, with the parameter being the mass of the body. Okay. Now how dangerous is the fact that at r equals 0 this thing blows up? Okay. It's not at all dangerous, because this equation will stop being valid long before you reach r equals 0. Okay. Now the whole point is we solve this assuming we are outside the matter distribution, some. The only assumption is that we are outside some spherically symmetric matter distribution. Spherical symmetry tells us that it depends only on, the potential will depend only on r. and thereafter this equation will tell us the dependence can only be 1 by r. Okay, and that's it.
It's not a point.
But it could be a point, but it needn't be a point. Okay, here, wherever we are, as long as we are far away from, so let's say the Earth. Okay, this equation is true if I am trying to find the Newtonian gravitational potential of the Earth. When is it true? It's true when r is greater than whatever 7,000 kilometers. Okay, and this is the answer where this is a fixed constant and this is the mass of the Earth and this is the distance to the center of the Earth. But it's only true if r is greater, so only true if r is greater than r tilde, the size of the distribution. And it doesn't really depend on the detailed shape of this distribution, whether it's all concentrated at a point or it's all spread out over a very diffuse sphere, as long as it's spherically symmetric and we are outside it. Okay? So what does it mean it's only true if r is greater than r tilde? It means if r was less than r tilde, that means we are finding the gravitational field inside the Earth, then of course this isn't true because I must put a density term here. Okay? What is the effect of that density term here? It actually causes this function, which has been rising in magnitude as I come closer to the Earth. Once I go through the surface of the Earth, it starts falling again smoothly down to 0 at the center of the Earth. We certainly don't expect a singular gravitational field at the center of the Earth. That would be nonsense because we would be extrapolating this to a place where the original equation is not valid.
So field should be 0 from the spherical symmetry actually at the center of the...
Well, infinity is also spherically symmetric. So the point is that from common sense, that this function is spherically symmetric, right? You're right. I mean, it should be 0 if it's not somehow badly behaved. This function says it's badly behaved. But that's just a silly application of this formula, which comes from this formula. And this equation itself is not true if you are inside a matter distribution. It's only true in free space. Okay. Now, all these things I'm telling you, surely you are not hearing for the first time. All of this you know. Moreover, the whole discussion is parallel if you have electric charges and electrostatic potential. All the equations are exactly the same, changing some constants and replacing mass by charge and maybe some signs. Yeah?
Sir, when you're saying it's true when r is greater than r, so we are taking a very big spherical shell inside which has a radius greater than the mass distribution.
Yes.
There. Also, is it not that the mass enclosed within the shell, which means that the rho equals to some finite value?
No. So this parameter is fixed by Gauss law, which counts the mass enclosed by the shell. That's correct. But how the mass is distributed inside where we are, we can't possibly know. If I give you a sealed ball and show you its gravitational field, you can't tell whether the ball has a continuous distribution of matter inside, or it just has a very heavy thing sitting at the center, or it's made up of concentric shells with gaps in between. You can't tell by any experiment on the gravitational field alone. That's the content of the statement. It's universal as long as you are outside the whole matter distribution. As soon as you are inside the matter distribution, this is far from universal. How it goes to 0 at the origin will depend on exactly what the matter distribution is. And there's a particularly weird case which we talk about as an idealization, where in fact it grows without limit because you have a point charge. But okay, point charge is not a very realistic thing. In fact, there is essentially no such thing. Everything has a finite extent.
So that is, how is that actually reconciling with the fact that rho equals to 0? The matter density is 0.
Yeah. For a point charge, because rho is q times delta 3 of x. So it integrates to a finite amount, but its actual value is infinite at a particular point. That's the mystery of the delta function. That's how it is. Okay, now why am I telling you all this? Because this suggests that it makes sense to study the general relativity analog of this Newtonian question. That's all you want to do. The physics is, initially at least, it's the same. Instead of taking source-free Newton equations, we take source-free Einstein equations. So we just set T mu nu equals 0. Okay. So the difference is merely the difference between this del square phi equals 0 and that whole left hand side equals 0. Moreover, we are guaranteed that for very weak phi, if we take this type of metric, that equation actually gives me this equation. So it's sort of something familiar for weak fields. What it will do for strong fields, we don't know. However, the key difference between these two cases is that this is a linear equation for phi, and this is the most horribly nonlinear equation in all of physics. Okay, why is it nonlinear? Because G is the amount of measures something like eta mu nu plus some deviation. In that deviation, G inverse is nonlinear, and G inverse appears all through that equation to define R mu nu and to define R, because it's even needed to define the Christoffel symbol. So it's a very nonlinear equation. Okay, anyway, whatever answers we get to that equation, so therefore now we are looking for a metric for G mu nu that solves R mu nu minus half G mu nu R equals 0. But this equation is very easy to simplify. Just contract it with G mu nu, G upper mu nu. So the first term becomes R, and the second term, G mu nu is 4. Okay, where if I take a matrix, multiply it by its inverse and take the trace, then it's trace of identity, which is 4. So I get minus 2R equals 0. So this tells me that R is 0. R is the Ricci scalar. That tells me that if this equation is true, this is true. This in turn tells me, plugging it back into this equation, that R mu nu must be 0. And of course, if R mu nu is 0, then R is certainly 0. Okay? So therefore, I can just try to solve the simpler equation. And a manifold which has R mu nu equals 0 goes by the name of Ricci flat. The Ricci tensor is 0, so it's called Ricci flat. Okay, it's not really flat. Really flat would be if the full Riemann tensor was 0. But Ricci tensor contains some partial information of the Riemann tensor, and that partial information has to be 0. So it's R mu nu equals 0. So that's the equation we're trying to solve. So is this chain of events clear? So we can replace this by this simpler equation. And now, the one more thing we know about the solution we are looking for is that we expect for large R. Okay. Let me say one more thing. We'll restrict to spherically symmetric solution for now. So we are going to try and solve the vacuum Einstein equation with a spherically symmetric solution. That's the analog of solving del square phi equals 0 and finding that phi goes like 1 over R. Okay? If you have a very bizarrely shaped body, then the Newtonian potential away from it doesn't go like 1 over R close to that body. It might go like it when we are very, very far, but just outside that body, it will have theta and phi dependence, and it still will solve del square phi equals 0. It's not a problem, but it's very technically annoying and difficult to find such solutions in general. So we look for the most highly symmetric one, and the most highly symmetric is the spherically symmetric solution, which means that the solution, the metric, will have exactly the isometries you would expect by spherically symmetric in space. So the isometries you would expect if you just rotate x, y, and z arbitrarily into each other. Okay. Another thing is, we expect that this solution we are looking for will reduce at large distances to that solution. I've written there in terms of the Newtonian potential, with the Newtonian potential being minus Gm upon R. So what is it? ds squared equals minus 1 minus 2 Gm upon R dt squared plus 1 plus 2 Gm upon R. Here I should write dx squared plus dy squared plus dz squared, but let me write the same thing in this way. Just notation. Is the metric of a 3-sphere written in this way? Not a metric of a 3-sphere, sorry, the metric of 3 space written in this way, the 3-dimensional Euclidean space. Instead of using Cartesian, I have simply used spherical polar coordinates. And what d omega 2 squared means is d theta squared plus sine squared theta d phi squared. So useful shorthand. So this is the metric of a 2-sphere. Okay, it's a way of thinking about 3-dimensional space as successive larger and larger 2-dimensional spheres. If you nest a lot of spheres, you'll get 3-dimensional space, and these are the natural coordinates for that. Okay, so these are what this we want to solve this, and we expect to find a solution that reduces to this, and we'll find a solution which is astonishingly simple, and it's an exact solution of R mu equals 0, and then we'll check that it reduces to this.
I mean, this works at very large distance.
Yes. Yes. I've written at large. Okay, and here we can see also what large R means. Large R has to have some distance scale, means R much greater than 2gm. However, there's the other criterion, which is that if this describes the metric, or the thing we are going to find, if it describes a metric of a real object, then it can only do that if R is also greater than R tilde, which is the physical size of that object. Because inside that there will be a matter distribution, then there will be a T mu nu, then this equation we are trying to solve isn't the correct equation in the first place. Same situation which is true in the Newtonian case. Okay, good. Now, before I actually start to do that, let me notice, this we'll notice repeatedly, that we can use coordinate transformations to make our life simple. Okay, this particular simple metric can actually be simplified further by the following observation. Let R prime be 1 plus Gm upon R times R, which is the same as R plus Gm. Just a shift in R by a constant. Okay. Now, Gm upon R is a small quantity because R is much bigger than Gm. So think about Gm upon R as being epsilon, and then this metric should be valid to first order in epsilon. Higher orders in epsilon don't mean anything. Okay. So if I do this, then R prime squared is R squared plus 2Gm R, and I'll neglect the last term, which is a higher order in epsilon. So this is R into R squared into 1 plus 2Gm upon R. So this shift of coordinates allows me to replace this factor multiplying R squared here by just R prime squared. In other words, the factor has got absorbed in this piece. What about its effect on the first piece? Turns out it has no effect because dr prime is actually equal to dr, because the two differ by a shift. Okay? So, in fact, what happens is, so dr prime is dr, so the factor simply stays there, but in terms of r prime. Okay? Now, if I replace r by r prime in the denominator, there will be some change from this, but it's of higher order in epsilon, so actually it's the same thing. In other words, what I am saying is that this change of coordinates gives me to the same order the metric which looks exactly the same as above, now in terms of r prime, plus 1 plus 2Gm upon r prime dr prime squared, plus, and the last term is r prime squared, I can put it here, Okay? So this is my claim that under the coordinate transformation on the right, that metric becomes this. What's the net effect? The factor in front of this term has got absorbed away. It's not there. So, but the factors in front of these two terms are the same as before. Is that clear? They're actually not exactly the same as before, but they differ only by higher order terms in epsilon, where epsilon is gm upon r. Okay? So we've simplified things. So we are looking for a metric which only has a factor in the first and second place, and it's trivial as far as the r squared t omega 2 part is concerned. And of course, this metric by inspection is manifestly spherically symmetric. It depends only on r's. There's no dependence on theta and phi. There's also no dependence on time. This is a stationary. This is in fact a static metric. There's also no cross term dt dr or dt d omega. So it's a static metric. Okay. So note. Also note that up to this point I haven't tried to solve Einstein equations. I am simply using Newtonian gravity correspondence to tell you what we should expect to find. Okay? But we shouldn't be too biased by it. We'll try to find a solution directly using only purely logical, straightforward methods. And only at the end we'll be happy to find that that solution has all the right properties. It matches on to this for large r, and in fact it is spherically symmetric. It is in fact static. The only prejudice we are going to put in is that from the start we'll assume it's spherically symmetric, nothing more than that. And I think this is my reading that this is what Einstein would have sort of expected, and what Schwarzschild did, which was new, was to say, okay, with these kind of things I'll find you an exact solution of r mu equals 0. Okay, up to now there's no reason on earth to think that there's an exact solution which has the property of reducing to this. You might, or no reason to think you might find an exact solution. Okay, there's a differential equation. It's non-linear partial differential equation. It has many solutions. What hope do you have of finding an exact solution? Okay, but I think the new thing that Schwarzschild did was to, in fact, assume there is an exact solution and work through the mathematics nicely to reform it. So now we will start to solve Einstein's equation, but not this whole mess, just a simplified version, r mu equals 0. And we'll start by assuming that the metric is spherically symmetric and nothing else. And whatever we find by doing this, we'll find exactly one solution, which is the Schwarzschild solution, and that's the most general solution of this equation under this assumption. That's quite remarkable. There aren't any other solutions of r mu equals 0 that are spherically symmetric, except the one we'll find today. That's even stronger statement, because it's a nonlinear differential equation. Okay, you're lucky to find one solution, but once you've found one, there could surely be millions more. Turns out, no. This symmetry is so powerful. For example, it prevents time dependence. We never said that it has to be time independent. Nowhere here I've assumed that it's going to be time independent, but it will turn out to be time independent. Okay, so let's proceed. Now I should mention that this derivation is done in many different ways in many different books. I personally like to do it in a way that's not extremely rigorous, but it should be very clear what assumptions we are making. So there'll be a couple of steps that a mathematician or even a rigorous general relativist might question. On the other hand, they are good enough for Landau and Lifshitz, so which is where I took this derivation mostly from. Anyway, let's do it. Okay. Now what can happen? How can we write a metric that's spherically symmetric and completely general? Spherically symmetric means two things. One is that the functions which appear in the metric cannot depend on theta and phi. That is the first thing. No dependence on theta and phi. As usual, you may be alarmed by the fact that, well, I can always introduce dependence on theta and phi by changing coordinates. Something doesn't depend on theta and phi, I spuriously introduce. That's also possible. But if it's directly symmetric, there will be one coordinate system in which it's not dependent on theta and phi, and it's in that coordinate system we are going to find the solution. Okay. In addition to that, okay, so let me write the most general metric. It's going to be f1 of r and t dt squared. I just put the minus sign without any loss of generality. Even that's not an assumption because I still don't know if f1 will be positive or negative. Okay. Then I'm allowing for a term f2 of r and t dt dr. Okay. Then I'm allowing for a term f3 of r and t multiplying dr square, and finally a term f4 of r and t multiplying d omega 2 squared. So my claim is that this is the most general spherically symmetric metric. Okay. And it's up to us now to take this metric and in principle calculate all the Christoffel symbols, and from there calculate all the Riemann curvature tensor components, from there calculate the Ricci tensor components, set each one of them to 0 and solve it. Now nobody ever approaches a problem like that by taking such a general metric. First of all, it's not diagonal because of this cross term. Secondly, it appears to be time dependent.
Sir?
Yes.
So we are assuming here only that the metric is spherically symmetric.
Yes.
Then why are we not keeping the dt d theta and dt?
Yeah, dt d theta I was just wondering about. I don't think you can have dt d theta terms. Because you see dt d theta is of course invariant under the Killing vector, which is the shift of theta. Because theta shifts by constant. Actually, there is there is no Killing vector under shift of theta. dt d phi. So there is a Killing vector under shift of phi. That is, so dt d phi is allowed for that. But there are two more Killing vectors. So there are three different rotations of the sphere, three independent rotations of the sphere. And if you check, dt d phi or dt d theta are not independent, are not invariant under all three rotations. Some of them may be invariant under some of the rotations. Okay, where these rotations are not constant shifts in theta and phi. If I shift theta and phi by a function, then d theta and d phi do change in general. Of course, that function would be such that this thing is preserved. That's the statement of spherical symmetry. That's the statement that they are Killing vectors. But dt d theta and dt d phi would not be preserved. While r, of course, doesn't get affected at all by rotations in theta and phi. So it's definitely preserved. Is that clear? So no dt d theta or dt d phi. It violates spherical symmetry. Okay. Now nobody actually starts to solve something like this without looking for coordinate transformations that simplify the metric. And the key here is look at the coordinate transformation allowed. So of course, also we don't want to spoil our life further by introducing theta and phi in the coordinate transformations when they are already not there. Okay, we don't want to make those coordinate transformations which complicate the metric more than it is. So we only allow coordinate transformations. R goes to r prime of t and r, and t goes to t prime of t and r. Okay, so these are two functions. Here we have four functions of t and r. So, modulo mathematical subtleties that could arise in principle, but actually can be shown not to arise, you can use these two transformations to fix any two out of these four functions. Okay, so we are going to use it to fix f2 of r and t to be 0. Thereby we have got rid of the only cross term, and now the metric will be diagonal. Okay, it will have dt squared, dr squared, d theta squared and d phi squared, and no cross term between any pair of coordinates.
So I didn't get the argument. How do you...
We have two functions at our disposal. So we use two functions to fix 2 out of the 4 arbitrary functions in the metric. We change coordinates like this to set any 2 out of these 4 functions to anything we like, which is reasonable. And what we are going to do is set f2 to 0, and we still have one more freedom. We'll use that to set f4 of r and t to r square. Okay. Now, it's not actually possible to set any function to any value you like, because at certain values there could be singularities. Okay. But this is a safe choice, because dt dr is not going to, if it's not there, it's not going to complicate the metric, it's only simplifying the metric. T lines are orthogonal to spatial directions. Basically what it says is that time direction is orthogonal to the space direction, while such a term, if it was present, would say that there's an angle between time and space. Okay. Similarly, setting f4 to r squared is a very good choice, because r squared d omega 2 squared is the angular part of the metric of 3-dimensional space. So if it's valid, if it's okay there, it has no singularity issues. If you wanted to set this to r cubed or r fourth or r or square root of r, you would very likely end up with some unphysical behavior in the metric.
But you're explicitly dropping the time dependence in F4.
No. Well, okay, now that's fine. F2, well, so am I dropping it here? I'm setting a function to a value, right? So I can set it to any value. You mean I'm not dropping time dependence
No,
here? I'm dropping
F4. F2 is okay.
F2 is okay, but I'm setting it to 0. So whatever time and space dependence it has, I'm removing it, right? So here what I'm doing is I'm removing all the time dependence and keeping a particularly chosen space dependence. The same amount of work. It's one function of 2 variables. This is a function of 2 variables, this is a function of 2 variables, this is a function of 2 variables, and this is a function of 2 variables. These two I can choose as I like. They will affect the metric by the usual metric transformation law under change of coordinates. I'm claiming the end result can be, these two can be chosen so that these two results are achieved. They are completely functions, they are not numbers. Okay, so I set the functions this way.
So this is just you're doing a Lorentz boost to get rid of the.
No, it's not a Lorentz boost. It's a general coordinate transformation. I mean general relativity. A Lorentz boost cannot be an arbitrary function of t and r.
Okay, sir.
Completely arbitrary function. The only issue is about singularities. If the function is 1 by r, then I better worry about the place r equals 0 very carefully. Okay, that's all. But it's otherwise, the whole point of general relativity is that I can transform my coordinates in an invertible way to any other set of coordinates by any function. Okay. And actually, I have a choice of 4 functions available to me, because I can have a function r, t, theta, and phi replaced by r prime, t prime, theta prime, phi prime of all 4. But I choose only to make these restricted coordinate transformations so as not to introduce any theta and phi dependence in the metric. If I wanted to introduce theta and phi dependence, it's perfectly legal, but of course it would only make my life worse. Okay. So there are no assumptions here. I'm simply using the freedom of the system to fix part of the system, and now I'm going to determine the remaining part which is unfixed by that freedom. And finally, I'm going to find the metric in one coordinate system, right? I cannot find a metric in every coordinate system. I can give it to you in one, and you can then transform it to any coordinate system of your choice. Okay. Good. Now that we are left with 2 functions, f1 and f3, we'll write the metric ds squared as we'll parameterize them in slightly different language. I'll call this e to the minus e to the 2 alpha of r and t dt squared. So all I've done is write f2 as e to the 2 alpha. You may object that in this way I've introduced the prejudice that f2 is positive. Sorry, not f2, f1 as e to the 2 alpha. So now I seem to be imposing that this is positive, f1 is positive, because I've written it as e to the 2 alpha. But I won't be fussy about whether alpha is real or imaginary. We'll see that later. Okay, so this could turn out to have, this whole exponential could turn out to be negative if I allow alpha to be complex. So we'll hold off on that. We are not going to impose our prejudices on this. Okay, next I'll rename the function f3 to beta. Same thing about beta. And then finally I'll just write r square d omega 2 square. So I hope you can see that the solution we are going to get will have a function multiplying dt square and another function multiplying dr square and nothing multiplying r square d omega 2 square. So we seem to be in very good coordinates to pursue this job. Moreover, it's going to match hopefully well onto the physical solution that we already found for weak Newtonian field, because that also had written in coordinates which had a function here, and nothing over there. Very good. Now, we can only go on talking so long without implementing Einstein equations. Sooner or later we have to agree to do some calculation, and this is the point where we start. So let's notice that the metric now, if I write it as a matrix, is diagonal minus e to the 2 alpha, e to the 2 beta, r squared and r squared sine squared theta. It being diagonal is very nice because g upper mu is also diagonal, and this is this. So no problem here at all. Whenever you need G inverse, you need it in all the formulae. That's it. The dt dr term would have made this inconvenient, though not impossible. Good. So now actually we've done this exercise in a few two-dimensional examples. We need to calculate all the non-vanishing components of gamma, the Christoffel symbol, and after that we plug it into the, so we plug this metric into the definition of gamma, then we plug gamma into the definition of 4-index Riemann tensor, and then we plug that into definition of 2-index Ricci tensor, and then component by component we set it to 0. So this is the kind of thing that probably most people don't prefer to do in class. Actually, if you want a good handle on it, you better do it yourself. But anyway, I'm going to do it in class, and I'm going to do it in, I hope, the shortest possible time. Except that I'll give you answers for things. Obviously, I'm not going to work out every single step. But let's see the answers for all the Christoffel symbols. So here is a particularly simple one. You get alpha prime. So here prime means d by dr and dot means d by dt. So much easier to write the formula once you agree on that convention. So this is d by dr or del by del r partial of alpha of r and t. Okay, so that's gamma ttr. Gamma t comes out to be alpha dot. Then gamma r t comes out to be beta dot. So I hope you agree that each one of these things I don't have to derive for you, but the derivation is extremely straightforward by applying the formula for gamma. And you can also see that some of the properties agree with what you would expect. So let's point those out as we go along. So how many gammas have we got by now? 1, 2, 3, 4, 5, 6. And these are only the gammas in the TR directions. So notice that they have no theta or phi dependence because they only involve GTT and GRR for their calculation. So therefore they should depend only on alpha and beta and on T and R derivatives of alpha and beta, and that's exactly what we do. The next set of gammas do involve theta and phi. Some of them are trivial in the sense you can see that this doesn't depend on alpha and beta. So this is what you would also get if you were doing flat space. Flat space is a special case of this solution where alpha and beta are 0. Okay. So that's this. Then there's gamma r theta theta. This one is minus r e to the minus 2 beta. Then there's gamma phi r phi. This is again 1 by r. gamma r phi phi. This is then gamma theta phi phi. And finally, gamma phi theta phi is cotan of theta. So that's the complete list of gammas. Notice that there is no phi dependence anywhere. Why is that? Yeah, G mu had no phi dependence, but there is a theta dependence. That's because of theta dependence is okay. It's because G mu had a sine squared theta term in it. Inside d omega 2 squared, there was sine squared theta d phi squared. So that theta dependence should be coming in here, and there it is. Doesn't conflict with the fact that there's a killing vector. There are 3 killing vectors on the sphere, because out of those 3, the only one which is a simple translation is the phi killing vector. It simply rigidly rotates the sphere. Phi is the coordinate defined around the z-axis, but theta is not the coordinate around some axis. In fact, the theta lines, as you know, all meet at north and south pole. They're all great circles. So there is no rigid transformation of the sphere along theta. So we don't expect that theta goes to theta plus constant would be a symmetry. It's not a symmetry of the metric, and it's not a symmetry of these things. But if you had worked out all the 3 killing vectors of the sphere, you would find that all of them would leave these things invariant. Good. The reason I'm saying this is that whenever you finish a calculation like this, you should stare at it and see that it makes some kind of sense. Okay. One of the nicest things here is that t, there's no gamma involving t as well as theta or phi. All those are 0. So all that I have, whatever I haven't written, are 0. If you remember an earlier lecture, I wrote down all the gammas for some 2-dimensional metrics, and I warned you that 4-dimensional are much more complicated. In fact, the number of gammas is 4 times 4 symmetric, which is 10. So 40. Okay. So is that right? Oh, that's an awful lot of gammas. Is it really 40? I think it is, huh? It is, huh? 4 times 4 symmetric. So there are all kinds of gammas that are 0, like gamma phi t theta, gamma phi t r, all kinds of gammas. Lots of them are 0. Most are 0, maybe only about a quarter of them are non-zero. Okay, good. So we should be happy. Good. Now we plug this thing in. From this, derive.
Is there a way you can actually look at the symmetry and predict which gammas will actually
be 0? Probably. It's worth a try. I'll actually suggest that, in the set of things that I would advise you all to think about when you go home and go over this calculation again, try to see. You might find things. One finds all kinds of things by looking again. So there might be many things you can predict. Supposing you were doing it blind, try to do it blind. You can start with that metric, with the alpha and beta, and then close the notes and see what you can do by thinking about it, and then see which ones you can calculate and so on. So the next step is to derive R. So this also has a number of components, but turns out actually the number of independent R's is less than the number of gammas. So it's actually easier to write down at the end. So let me write down the number of all the non-vanishing R's for you. So one of them is R, T, R, T, R. So I'm going to write the ones with first index up and remaining 3 down, because these are easily derived from the Christoffel symbol without any raising or lowering extra. Okay. Since finally we are going to set the Ricci tensor to 0, it hardly matters whether we calculate the guys with indices up or down. We're just going to set them to 0. Of course, we'll be tracing this to get the Ricci tensor. That will be another step. Good. So this gives me e to the 2 beta minus alpha beta dot into beta dot minus alpha dot plus beta dot dot. Plus these three functions of alpha and beta. This is the only somewhat lengthy one to write, the others are much simpler. So this one is minus r alpha prime e to the minus 2 beta, then r, okay, e phi c phi, similar, just with an extra factor of sine squared theta. Then there's r theta, r theta. This is roughly, you begin to see the pattern. They involve some powers of r and sine squared theta, and some alpha primes or alpha dots, beta primes, beta dots, and some exponential factors which will always be of the form e to the minus 2 beta or e to the minus 2 alpha or some combination of those. Good. Then this one is again the same as the one above with the sine square. Then what's left? Theta phi, theta phi. This is slightly different pattern, but equally simple. There. Now we've got most of the R's, so let me just check. There are 5 of them I've written down. There are 2 more that slightly don't fit this pattern. In this pattern, you see that there are only 2 distinct indices in each of them. It's t and phi occurring twice each, or r and theta, r and phi, theta and phi. Like that. Okay. There are 2 more Riemann tensors that are not of this type, and they involve some mixture between t and r as well as the angles. So t theta r theta, and then t phi r phi. And again, no surprise, they are quite closely related to each other. This one is minus r beta dot e to the minus 2 alpha, and this is the same with a factor of sine squared theta. So that's all the Riemann curvature tensors for this metric. All the others are 0. So examples would be r, t, theta, r, phi. Principle you have to calculate it. Turns out that in this case it's 0. Or t, r, t, phi. Lots of them. So that's the complete set of Riemann curvatures. Now what shall we do to get Ricci tensors out of these? We have to just contract. So for example, if I want, now I'll do something that's convenient to me. I'll calculate r with one index up and one down. Again, setting this to 0 is exactly the same as setting the thing with both indices down to 0. So to do this, I actually need to contract with g theta theta, g upper theta theta on that, g upper phi phi on that, and g upper rr on that, and then sum all of them. Okay? There must be other ways to do it. This is the way I did it. Anyway, the answer is interesting. That's the answer for RTT. It's a little more complicated, although you can clearly see that it's made up of the building blocks which we have already encountered. It's just combinations of terms which are already visible, but because of some inverse metrics and so on, you get things like this 1 over R behavior over here. The nice thing is that RR turns out to be very similar. In fact, it's almost the same. The first term is the same. And the second term is also mostly the same. Okay, that leaves R theta theta, which will come out to be exactly equal to R phi phi. So both are the same expression, and that expression is 1 by R squared into e to the minus 2 beta bracket that. And now we are almost done. There's just one more. So four Ricci tensors I've got TT, RR, theta theta and phi phi. Can you guess which would be the fifth one? There can only be one more. No, T theta will not be there. TR is there. Because we have some Riemann tensors which involve a T and an R and then two thetas or two phis. Okay, two thetas or two phis can be contracted. Remember, the metric is diagonal. Okay, so when I contract those two thetas or those two phis with an inverse metric, then I'll get a contribution to RT. Okay, and there's no other R in the problem. That's the last one, and is in some ways the most important because it immediately gives me a very striking result. First of all, it leads to the only equation that we can solve without any work. That's it. So now it's all the R's are on the board, and now I have to set all of them to 0. The only thing is to do it a little bit cleverly so that I can solve the resulting equations. So what does this one tell me? I already learned that beta is time independent. Okay, so Einstein equations imply the following set of things. First, beta dot equals 0, so beta equals beta of R only. Okay, now it's up to us how we proceed with the others, but what I'll suggest is take these two, TT and RR, and let's subtract them and put that difference to 0. Of course, each is 0. But the difference is also 0, and difference is great because all this junk disappears. Anyway, all this junk has disappeared because beta dot is 0. We've just established that. Okay, but also most of this junk will disappear, and we'll only get alpha prime plus beta prime equals 0. Okay, that's a nice equation. Let's solve this. So this tells me that alpha of T and R plus beta of R is equal to some unknown function f of t, integration constant. Okay, it's an integration constant in R, but it can be, of course, dependent on t, the partial differential equation, right? Functions of two variables. Okay, now let's remember something that perhaps we had not thought much about. We thought we had used up our general coordinate transformations of T and R. Okay? But actually, if you recall the form of the metric, ds squared equals minus e to the 2 alpha tt squared plus etc. T going to t prime of t doesn't disturb the form of Jackson. Of this metric. I'm not allowing it to be a function of t and r, only I reparameterize time by itself. Okay. All the other stuff in this has no dependence on time. Neither there's a dt nor there's a function of t in it. Okay. In particular, beta is now constant. So in time, so through this equation, so I didn't worry about anything happening to beta also when I reparameterize my time. But it will have an effect here. What effect will it have here? We can work it out, or we can just say it in words much faster. So its effect is to shift alpha of t and r to alpha plus some arbitrary function of time. What will that arbitrary function be? It will be dt by dt prime squared, then take the log to put it in the exponent, whatever it is, some function of time. Okay? By choosing this as some particular function of time, I can generate any function of time to add to alpha in the exponent. Is that clear? Because it's multiplicative function, but multiplicative means it adds to alpha in the exponent. Okay? So I like to do things this way. Other authors will go through the thing very painfully for you. Dt is dt by dt prime, then I take put it in the exponent, and I show you what function of dt by dt prime is g. But you can figure that out. It's whatever it is, we don't care. The point is we can generate any function g we like. Okay. That means that I can use that time going to a new function of itself to remove f of t. I'll just choose g such that alpha is shifted in such a way that it removes this f from this equation. And now we have alpha of t and r in these new coordinates plus beta of r equals 0. In other words, the integration constant that we introduced here, constant as a function of r, turns out to be trivial because can be removed by reparameterization of time, and we get this equation. Now at every step, if I want to be very, very painful, I can say, well, no, this is really in the time coordinate t prime rather than t. Okay? But we need not be possessive about our coordinates. There's no point saying these are the coordinates of 15 minutes ago and these are the coordinates of today. Whatever coordinates we are working in are the coordinates of today. And those ones we'll write without a prime. Okay? Maybe we'll write it with a prime and then we'll say, okay, now we drop the prime and rename t prime back as t. But you have to understand these things. Okay, so what does this tell us about alpha now? Of course, this proves that alpha is only a function of r. And it's equal to minus beta of r. So alpha is independent of t. So we did it in two steps. Beta is independent of t was an Einstein equation. Alpha being independent of t and equal to minus beta followed from integrating some other Einstein equation and using a coordinate reparameterization to get rid of some time dependence. Okay? Notice that by now, without still knowing the functional forms of alpha and beta, our metric is static. Because what is static? Static is that it has no components g0i, which means no cross terms like dt, dr, and the component in that coordinate system, the functions are all time independent. Having no cross term is completely trivial. We just used, in fact, I must tell you that some of you objected to me setting that cross term to 0 today, but few lectures back you agreed to it when I called it g0i and I told you we can choose coordinates to set g0i equals 0. That day you agreed to it. So in future, if you agree to something in one lecture, you are obliged to agree to it in all future lectures. Okay? Actually, and that's a joke, you should always ask if you are not convinced. Anyway, so setting g0i equals 0 was not a clever achievement, but in that coordinate system where g0i is 0, alpha and beta are time independent, there is no other time dependence in the metric, therefore the metric is actually static. In this way, we have actually proved a side theorem which has an existence all its own called Birkhoff's theorem. Birkhoff's theorem says the most general a spherically symmetric solution of Einstein's equation is always static. Now, I don't know if I'm saying it exactly right, but whatever the theorem says, that's what we have proved. And if you want to see the exact statement, some books prove it separately and do the rest of the things separately, but I've tried to do it together, and we finally reduced ourselves now to a metric where we only have to determine one function of one variable, alpha of r, and we are done. How are we going to determine that? Well, we have plenty of equations still available. Actually, it turns out we have two equations still available and they turn out to be the same. We haven't used this equation, we are going to use it now. Alternatively, we could use some other linear combination of the previous equations, but it would give the same result. So let's do it. So to determine alpha, okay, so this equation says e to the, so I'm replacing beta by minus alpha from now on. So e to the 2 alpha into minus 2r alpha prime minus 1 plus 1 equals 0. This, I just said beta to minus alpha. So now it's an ordinary differential equation of a function alpha of one variable. So at least can be solved. In fact, what's surprising is that the solution is so simple. If I take this to the other side, I can write it as d by dr of r e to the 2 alpha is equal to 1. Because if I differentiate in r, I get just e to the 2 alpha, which is that. If I differentiate the exponent, I get 2r alpha prime times the exponent, which is this term, this on the other side of it. So it's that simple. So now I can integrate it, and the solution is that r e to the 2 alpha of r is r plus a constant of integration, which I will call minus r naught. Again, I don't want to prejudice you that it's negative in value. That we'll fix later. I'm calling it minus r. We'll see what is the sign of r. Okay. This in turn tells me that e to the 2 alpha r is 1 minus r naught upon r. What a nice and simple function. And this in turn finally gives me the metric in terms of this unknown integration constant r naught. Then the metric is minus. Notice now that in fact this thing, as long as r is greater than r naught, which is the integration constant, this will be positive. If r is less than r naught, it will be negative. So as I told you, I had no prejudice what is the sign of e to the 2 alpha. And I haven't put in any prejudice into that. So the answer is this. Plus, now the next term is e to the 2 beta, but beta is minus alpha. That means it's 1 over this factor. So it's dr squared upon 1 minus r naught upon r. And the last term, of course, can't be doing anything exciting. It's that. There it is. And this is called this Schwarzschild metric. And it's done. It's done mathematically. We still have to do some work to give a physical interpretation to understand what is R naught and to understand what kind of space-time this metric describes. Yes?
Removal of the cross term.
Yes.
The point is, in general, if you go to synchronous coordinates, the diagonal terms can become time dependent.
Yeah, we are not going to synchronous coordinates.
Here,
synchronous coordinates require you to remove g0i and set g00 equals 1. That means setting alpha equals 0. The valid choice of coordinates, but those are not the ones we are making. In fact, we are not set alpha equals 0, alpha equals 0, right? Alpha is the most important part of our solution.
here are we saying that the spherical symmetry allows you to remove cross terms without introducing time dependencies in every other dimension?
See, spherical symmetry is not what spherical symmetry does not allow me to do what you say. I am trying to solve Einstein's equation r mu nu equals 0. I can remove the cross term anyway. Having removed the cross term, if I now plug in my metric into Einstein's equation, my spherically symmetric metric into Einstein's equation, that equation determines that it's time independent. It's Einstein's equation which gave me beta dot equals 0, otherwise beta dot needn't be 0. It's not coming from any symmetry, it's coming from the dynamics of Einstein's equation. G0I equals 0 is certainly coming just from coordinate reparameterization. After that, you could have not told whether we were going to get time dependent, time independent, oscillating, fluctuating, rotating, gyrating, or anything. But after plugging it into this equation, all the dust settles and time dependence of everything in the metric is gone because of Einstein's equation. Nothing more to be said about it.
Isn't this staticity that we have got a consequence of spherical symmetry?
No. Consequence of spherical symmetry and Einstein's equation. Now, therefore, it's a consequence of spherical symmetry and it's a consequence of Einstein's equation. Therefore, if you didn't have one or you didn't have the other, then you wouldn't have the result. The consequence of two things, not of any one of them alone. There are solutions of Einstein's equation which are not static and not spherically symmetric. There are spherically symmetric metrics which are not static but then they don't solve Einstein's equation. Not a consequence of symmetry. Okay, good. So here's the most beautiful metric in the world and now we need to understand it. Of course, the board was not big enough for me to keep the formula which for the approximate form of this metric, but I think what you can see now is that the exact metric is remarkably similar to the approximate form we were expecting. So let's first rewrite the exact Schwarzschild metric, which was at the bottom of the board. And now let's remind ourselves what we were expecting to find by solving vacuum Einstein equations, which for large R should match on to vacuum Newton's gravity. And vacuum Newton's gravity would have given me approximate solution minus 1 minus 2 gm by R dt squared plus 1 plus 2 gm by R dr squared plus R squared d omega 2 squared. Now do these two match for large R? If they don't, then we are sunk. We don't really have any room to wiggle out of this embarrassment because all of these are dictated by principles that we have been advertising from the start of this course. So they better match. Okay, so I hope you agree that if we identify the integration constant R naught of the Schwarzschild solution with 2gm, and it also has a name, it's a particular radius, so it's called the Schwarzschild radius. M is the mass of the body whose gravitational field we think that we have found, although we never actually looked inside the body, we simply found the gravitational field outside. In Newtonian physics, we would have used Gauss' law to determine that the mass of the body has to be the integration constant. Here instead we matched on to Newton's gravity from general relativity and determined the integration constant. But either way, it's not a surprise that it comes out to be the mass. Okay. If we got any non-trivial solution of Einstein's equation in vacuum, it better be associated with the mass of something. Otherwise it would be rather absurd. There would be a gravitational field which was just there for no reason. Okay. So this is good. So this allows us to replace the Schwarzschild metric. In future it will be written with 1 minus 2 gm over R and 1 minus 2 gm over R. And when this factor is small, the denominator can be approximately written as 1 plus 2 gm over R, which is this. So this is how these two factors actually agree with each other at large R. Okay, this is just the first order power series expansion of that. However, miraculously, this and this are not approximately equal, they are exactly equal. Just so. Now you should also be careful not trying to read in too many properties of this metric because we found it in one coordinate system. You might ask, well, why did this factor come upstairs here and downstairs here? Well, if you go to another coordinate system, they can do various other things. Okay? So there's not always a meaning in looking at the metric. Just the metric in one coordinate system. There are still things you can do to upset it. You can, for example, redefine r prime as a function of r. Okay? And things will change a lot. It's up to you. But this is a very convenient form. Okay. Now the physical interpretation. So, based on everything we've said, this should describe the gravitational field of any. This describes the gravitational field in general relativity by specifying the metric for any outside any spherically symmetric body. Body means really any matter distribution whatsoever. It can be dust, particles, you name it, of total mass m. So does it describe the gravitational field outside the Earth, for example? Yes or no? No. Who said no? Why? It's not spherically symmetric. Why? If you are referring to the fact that the Earth is approximately flattened at the poles, then you are being a mathematician. The Earth is not spherically symmetric for a much more profound reason. It's approximately spherically symmetric for the, if you ignore the flattening. Yes, thank you. Somebody at the back is doing this. The Earth is rotating. A rotating body is not spherically symmetric. Why?
It has an axis.
It has an axis. Very good. So, if you ignore both the flattening as well as all the skyscrapers in Cuff Parade as well as the rotation of the Earth, then this will describe the metric far away from the Earth. Okay? Good. So let's imagine that this is being applied to the Earth. So this tells us that the Earth must have a Schwarzschild radius. What radius is that? It's 2gm. M is whatever is the mass of the Earth. Who knows the mass of the Earth here?
6,000
6 into 10 power 24 kg.
Very good.
Sorry, I
What? Sorry?
6 into 10 power 24
6 into 10 to the power 24 what?
kg.
Kg. How many people vote yes for that? I don't know what's the answer, so I'm not going to vote. If one vote you have in your support, how many vote against it? How many feel the Earth should be massless? Okay, so whatever it is, you can plug it in and you get, so for the Earth you find its Schwarzschild radius, and how much is it? R0 is equal to, anyone know the answer to this? Guess, random guess. A centimeter, who said that? Very good, it's extremely close. 9 millimeters. That's the Schwarzschild radius of the Earth. Okay. So, does it mean that this is the metric of the Earth down to a distance of 9 millimeters to the origin, to the center? No, because this is valid as a metric of the Earth. There's another radius that the Earth has, which I believe is 6,700 kilometers. There's some name for it which I can't remember, but I'm calling it the physical radius. There's some better name somewhere. But it's basically the radius over which there's a density. It may be more than that if you want to count the atmosphere and all the. You have to go very far away, perhaps. But anyway, something like this. So now we learn that the Schwarzschild metric is good is good for the Earth, if R, the actual radius at which we are looking at that metric, is greater than 6,700 kilometers. So there is absolutely no sense saying, sir, this is the metric of the Earth, what happens when R is equal to 2 gm, which is 9 millimeters? The answer is it's not the metric of the Earth when R is less than 6,700 kilometers, because after that we have to solve a different equation called Einstein's equation with an energy momentum tensor, which is that of the Earth. Okay? So there is nothing mysterious about this space-time metric as long as we use it to describe the Earth or indeed any body for which the physical radius r, which is the radius up to which there is a non-zero matter density, is greater than 2 gm, is similar from this point of view. Again, it should be spherically symmetric, and that's all. It's actually very nice because, like in Newtonian gravity, this gives you a universal answer for everything, requiring only a minimal property that is very symmetric. Okay, but of course, requiring that you are outside the body, because otherwise, how do you know what the gravitational field of the body is when you don't know what its energy density and distribution of matter is? If you want to solve the equation inside the body, you better know that. Okay, now all this to say that there could be objects, but they would be very strange and very unlike the Earth or the Sun, for which the physical radius is less than 2 gm. So the way we think of it is that here's a body which has a natural Schwarzschild radius governed by its gravitational field, and the entire body, whatever matter it contains, has gone inside that radius. Now something very non-trivial happens, because as you see, this metric then should be valid for all r going down to that value of r tilde, but in particular r can cross 2 gm and even go below it, and very strange things happen or appear to happen. So we'll discuss these next time or the time after that. But some of them you can see by inspection. For one thing, at r equals 2 gm, the coefficient of dt squared vanishes. But that coefficient is g00, and if you remember, 1 over root g00 is the amount of redshift, so it means the redshift becomes infinite. That's one thing that happens. Secondly, if r crosses 2 gm, then the sign of that thing changes and it becomes plus 1 minus 2 gm over r dt squared. However, the sign of the next term also changes. Next term is not 1 plus 2 gm, but is the one above that, the exact one. Remember, this approximate solution can't be used anymore when we are near r equals 2 gm. The sign of the next term also changes obligingly, so the coefficient of dr squared becomes negative. Okay. Now, when we are given a metric, it's not up to us to decide which coordinate is time and which coordinate is space. Time is whatever has the negative signature in front of it. If they flip, it means that after r equals 2 gm, once we go inside, what we used to call time has become space, and what we used to call space has become time. They've interchanged roles. It's lucky that they've interchanged. If both of them had become space-like or both had become time-like, one doesn't know what one would have done. But at least they interchanged roles smoothly, sort of. Okay, not very smoothly though, because at r equals r0, the space part dr squared, its denominator becomes 0, so it also seems to blow up. Okay, so space intervals become very large, time intervals become very small, very strange thing. So we'll need to look at all of those in the future. But I just want to say, it's already interesting when r is much larger than r0. Okay, because if we cut out the distraction about what happens when we go too close to this strange thing which is collapsed inside this Schwarzschild radius, we've got the gravitational field in general relativity for any spherically symmetric body, and what we should do is to find out how an experiment would detect such a field? And the answer is pretty obvious. You would have a particle outside any given body and it would have orbits, it would have trajectories in this metric, which are the geodesics of this metric. And we can calculate those and we can go out and measure how particles actually behave in the field of gravitating objects. And either we find the Newtonian predictions or we find departures from those. If we find departures, do they agree with this thing we found? And then of course we have confirmed general relativity. So that's first. Then the exotic stuff, what happens when we get very close? That's a different level of question altogether. It's not realizable near the Earth, for example. But the first question is very much realizable because things travel around the Earth or around the other planets, and light in particular, and we can, the famous deflection of light or precession of perihelion or Mercury, these experiments all come from finding orbits in this metric. So that's what we've done with this. Okay. Okay, I'm done. Please go away. Thank all of you for not asking me when I'll correct your homework. It will make me embarrassed, so I'm going to try and do it soon. Videos. Assignment. Take it back, yeah?